we know that we have a vector space. It means that we have a set, right? And then in that set we can define the multiplication by a scalar. If we take little b in capital B, then this should be an element in B. And if you take two elements in capital B in the set, there should be an operation that allows you to add these two, and there must be some properties that needs to hold true in order for this to be a vector space. Then we're going to say that W is a subspace of B, assuming that V is a vector space, if W is contained in V and W with the operation that it has because it's contained in V, then W is a vector space. That means that when we think about the elements in W, then this element satisfies all these properties. Basic examples. Then we have that, for example, W equal V is a subspace. We have that trivially W is contained in V and is a vector space because W is equal to V. Another example is W equal to the zero vector in the vector space. Notice that we can see that this vector on its own satisfies all the properties. If we multiply by a scalar, we get an element in W. There is only one element in W. And if we take two elements in W, but there is only one, if we add 0 plus 0, then we get that this is equal to the zero vector, which is an element in V. And we can check that all the properties are true. Let me just provide another example of something that is not a subspace. We have that R2 is a vector space if we use as scalars the real numbers. We are usually using as scalars either the real number or the complex numbers. Then this is a vector space, and let's take these 4 points. This point, this point, this point, this point, and this point. Actually, these 5 points. Then our W is just the vector 0, 0, 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Is this a subspace? Then in order to be a subspace, it has to be a vector space. And to be a vector space, the addition must be defined. But look at this. We have, if we pick B1 to be 1, 0, right? 1, 0 is an element in W. And if we take V2 to be 0, 1, 0, 1 is an element in W. Then if it is a vector space, the sum must be in W. And then in this case, the sum B1 plus B2 is 1, 1, which means that the sum is not defined in W, right? And therefore, it's not a vector space on its own. And for that reason, this example, that this W is not a subspace. There is a theorem that allows us to easily check that a subset is a subspace of a vector space. Notice that in principle, we have to check 2 things. One, that is contained in V, and the other thing is that it's a vector space. That means that we have to check all these properties. But since most of these properties holds true because V is a vector space. For example, B1 plus B2 equal B2 plus B1. That holds true because it holds for every vector in V, and then since W is containing V, then it holds true for vectors in W as well. The following theorem allows us to check if a subset of V is a subspace. Let's say theorem. If V is a vector space, then W containing V is a subspace if 1, for every scalar alpha and every little w in capital W, we have that alpha W is an element in W. And the other property is that if W1 and W2 are elements in W, then W1 plus W2 must be an element in W. Look how this subset of R2 fails the second property, right? I took this vector, and when I add them, I didn't get a vector in W. Actually, we can show that every subspace either is this one, which has only one element, or it will have infinitely many elements. Let's see another example. Let's take W to be the set of n, m, such that n and m are integers. Then is W a subspace? We have that actually the second property holds true. If we take like an element in W, it will look like this, right? This is an element, a vector W1 in W, because with these two integers. And if we take this element, then when I add them, I get n1 plus m1, n1 plus n2, and m1 plus m2. And since the sum of integers is an integer, then this vector is a vector in W. But we can see that property 1 doesn't hold true. Let's take, for example, W equal 3, 5, right? This is an element in this W, because the definition of W says every pair with the property that the entries are integers. But then property 1 says that I can take any scalar. Let's take the scalar square root of 2. If we take alpha equals square root of 2, because of this property, if W were a vector, a subspace, then we must have that the square root of 2 times 3, 5. It should be an element in W, but this is 3 square root of 2, 5 square root of 2, and this is clearly not an element in W. Therefore, W is not a subspace. Is W a subspace? The answer is no, it is not. Let's provide more examples of subspaces. Before doing that, let me provide the following definition. And it says, let's suppose that V is a vector space. And let's suppose that S is a subset of B, but in this case we're going to assume that S it has just finitely many elements. And then we're going to denote the span of S. This is going to be the notation for that, and it's going to be the span of S. And it's just the set of linear combinations of the elements in S. That means that they are elements of the form x1 b1 plus x2 b2 plus xk vk, such that the x to I are scalars. I write scalars because they could be the complex numbers or the real numbers. As an example, if V is R2, let's write example here. Example 1. If V is R2 and S is the set with only this vector, then the span of S is going to be the vectors of the form x1, 1, 1, such that x1, let's suppose that we're working in the real numbers, and in this case this set is easy to visualize, is this line. Then S has finitely many, and if S has a non-zero vector, then the span of S has infinitely many vectors. Right? Another example, if we have that V is R3, and let's suppose that, let's call it T now. T is the set that has these vectors 1, 0, 0, 0, 1, 0. Then the span of T is just the linear combinations of these two vectors, x1, 1, 0, 0, plus x2, 0, 1, 0, such that x1 and x2 are real numbers. And essentially, these are the vectors of the form x1, x2, 0, such that x are real numbers. And we can see this geometrically. If this is x1, x2, and x3, that means the third component is 0. That means that we're working in the xy plane or the x1, x2 plane. Then there's the notion of the span of a finite collection of vectors. There are finitely many elements in S, but the span of S has infinitely many elements. Let's do an example with matrices. Just to consider S to be the matrices 1, 1, 0, 1, 0, negative 1, 1, 1, 3, 0, 1, 4. And let's consider the span of S. Then this is contained in the set of matrices 2 by 2. But then a good question to ask is the span of S, the span of these three matrices, equal to the whole 2 by 2 matrices? Let's try to answer that question. Then let's start with an easier problem. Then let's start with this question. Is 1, 5, 0, 1 an element in the span of S? And in order to solve this question, then we need to ask ourselves, can we find weights such that this matrix is a linear combination of these three? And then it will be, can we find three weights, x1 plus x2 plus x3, 3, 0, 1, 4 equal to 1, 5, 0, 1. Then the left hand side becomes the matrix x1 plus 3x3. The second entry will become x1 minus x2. This entry will be 0, x2 plus x3. And this entry would be x1 plus x2 plus 4x3. And we want this to be 1501. That means that we want to solve the following system. x1 plus 3x3 equal 1. x1 minus x2 equal 5. x2 plus x3 equal 0. And x1 plus x2 plus 4x3 equal 1. The augmented matrix for this system is 1, 0, 3, 1, 1, negative 1, 0, 5, 0, 1, 1, 0, and 1, 1, 4, 1. And if we do row reduce, we get that this matrix is row equivalent to the matrix 1, 0, 0, 7, 0, 1, 0, 2, 0, 0, 1, negative 2, 0, 0, 0, 0. And therefore the solution for this system would be x1 equals 7, x2 equals 2, and x3 equals negative 2. That means that this matrix can be written as a linear combination of these three, and for that reason this matrix is in the span of S. Let's check that. 7 times 1, 1, 0, 1 plus 2 times 0, negative 1, 1, 1 minus 2 times 3, 0, 1, 4. And then what matrix is this? We have 7 plus 0 minus 6 is 1. 7 minus 2 is 5. Plus 0 is just 5. 0 plus 2 minus 2 is 0. And 7 plus 2 is 9. Minus 8 is 1. Then indeed we have shown that this matrix is in the span of S. But then how to prove if the span of S is the whole set of matrices? Essentially what we need to show is that every matrix A, B, C, and D can be written as a linear combination of these three matrices. Let's see what happened. When we do that change, then this changes into A, B, C, and D. And here we will have A, B, C, and D. And the only difference is that here we cannot use the calculator to do row reduction. And let's see, we get, instead of this 1501, we will get A, B, C, and D. But then we can do this by hand. Let me erase this part, and let's do row reduction in this direction. Let me change row 2 by adding negative row 1, and let me change row 4 by adding negative row 1. Let's use this pivot to put zeros here and there. Then we have 1, 0, 3, 8. When I do this minus this, I get 0, negative 1, negative 3, and I get B minus A. Here I get 0. Well, this row stays the same. 0, 0, 1, 1, C, and this one will be 1 minus 1 is 0, 1 minus 0 is 1, 4 minus 3 is 1, and D minus, and we get here D minus A. The only difficulty is that we have to do row reduction, but we need to deal with these generic variables. What row operations can we do here? We can use this -1 to put zeros here and there, and then we're going to change row 3 by adding row 2, and I'm going to change row 4 by adding row 2, and then we get the matrix 1, 0, 3, A, 0, -1, -3, B minus A. I'm going to do the sum of these two, then I get 0, 0, -2, and here is B minus A plus C. And here when I do the sum of these two, I get 0, 0, -2, and here I get B plus D minus 2A. Let me erase this. And finally, I can use this to put this pivot to put a 0 here. And then I'm going to do row 4 by adding negative row 3. Then this is 1, 0, 3, A, 0, -1, -3, B minus A, 0, 0, -2, B minus A plus C, and 0, 0, and doing this minus this, it will be 0. And when I do this minus this, I get the B's goes away, and I get -A. -2A plus A is -A plus D minus C. This means that if we select A, B, C, and D such that this number is different from 0, then when we do the whole process, we will get an inconsistent system. Just as an example, if we change this by, let's say, 1, 1, 1, 1, right? Then we will do this process. We're going to be asking ourselves if we can find x1, x2, x3 such that we get 1, 1, 1, 1. And then we will be solving this system. 1, 1, 1, 1. And then here we have the column 1, 1, 1, 1. And for this one, we don't have to do row reduction by hand. We can just use the calculator, and we get that this is row equivalent to the system 1, to the matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, which means that this goes with the system x1 equals 0, x2 equals 0, x3 equals 0, and 0 equals 1. That means that this system is inconsistent, and therefore this matrix cannot be written as a linear combination of these three. We can go a little further and say that this space is just the collection of matrices A, B, C, and D, such that -A plus D minus C is equal to 0. Okay, we have this example, and let me mention a theorem that is very, very important, and is that in general, the span of any set is a subspace. And let me write that as a theorem. The span of a set S, that means this space, is a subspace. Let me just we're claiming that these two sets are the same. How do we show that this is a subspace? Let's just do an example. Let's suppose that we have the matrices A, B, C, D, such that negative A plus D minus C is equal to 0. How do we prove that this is a subspace? We need to pick a matrix there, a generic matrix. And we need to prove that if we multiply it by a lambda, then what matrix do we get? We get lambda A, lambda B, lambda C, lambda D. And then we need to show that this, let's call this the space W. We need to show that this matrix is in W. But to prove that this matrix is in W, we need to show that it satisfies the property that allows it to be in W. What is that? That the first entry, which is negative lambda A, plus the entry to 2, which is lambda D, minus the entry to 1, which is lambda C. We need to prove that this is 0. But notice that this is just lambda times negative A plus D minus C. And we want to show that this is 0. But this is 0 because we know that this matrix, we start with a matrix in W. And since this matrix is in W, then this negative A plus D minus C is 0. Therefore, when we multiply by lambda, we still get a matrix that satisfies the equation. Same thing if we have two matrices. Let's say A1, B1, C1, and D1, and let's say A2, B2, C2, and D2. Let's suppose that these two matrices are in W. That means that to be in W, that means that negative A1 plus D1 minus C1 is 0, and negative A2 plus D2 minus C2 is 0. But then we need to prove that if we pick two matrices in W, then when we add them, it's still a matrix in W. What do we get? We get the matrix A1 plus A2, B1 plus B2, C1 plus C2, and D1 plus D2. But why this matrix is in W? Because when I do this entry, negative A1 plus A2 plus this entry, D1 plus D2 minus this entry, C1 plus C2, we can correct the first entry here. We get negative A1 plus D1 minus C1, the first entries, plus negative A2 plus D2 minus C2, and this part is 0, and this part is 0. For that reason, this is 0, and that means that this matrix is in W. Then we have that this set is a subset. We have that this subset is a subspace of the matrices 2 by 2. Let's end by writing this subspace as the span of some matrices. Notice that we already know that they are equal to the span of these three matrices, but let's pretend that we don't know these three matrices and we want to write it as the span of some matrices. How can we do that? Then essentially what we're going to do is we're going to solve this system. Negative A plus D minus C equals 0. Remember that here the variables, let's pretend that the variables are A, B, C, and D. Right? These are the variables. Then the A is a basic variables. And I have three free variables that are B, C, and D. Then I can write A, the basic variables in terms of the free variables, and I can write A equal D minus C, and that means that the matrix A, B, C, D, right? Since it is in W, then A must be equal to D minus C, and then I have B, C, and D. Everything is written in terms of the basic variables, and I can write this as, let's say, B times the matrix 0, 1, 0, 0, plus C times the matrix negative 1, 0, 1, 0, plus D times the matrix 1, 0, 0, 1. And that means that this space W can be written as the span of these three matrices. 0, 1, 0, 0, negative 1, 0, 1, 0, and 1, 0, 0, 1. Maybe it is a good idea to do another example like that. Given a subspace that is written as a set of equations, how to write it as the span of some vectors. Let's have W equal to the matrices of the form A, B, C, D, E, F, such that A plus B plus C plus D equals 0, and C plus D plus E plus F equals 0. And these are two equations. Here is and let's try to write this subspace as the span of some matrices. Notice that here we are thinking that this is a subspace of matrices 2 by 3. What can I do? We can solve the system of equations. A plus B plus C plus D equals 0. C plus D plus E plus F equals 0. Notice that the matrix of this system, in this case the variables are A, B, C, D, E, and F. Then the augmented matrix of this system is 1, 1, 1, 1, 0, 0, 0. And here we have 0, 0, 1, 1, 1, 1, 0. That means that the basic variables are A and C, and the free variables are B, D, E, and F. Then let's write the basic in terms of the free. And we can do that by saying, start from this one, we have that C is equal to negative D minus E minus F. Are these free variables? Yes, they are. And from here we have that A is negative D minus C minus B. Are these free variables? No, I have to replace this C, and I get negative D minus negative C, but C is negative D minus E minus F minus B, and then the D's cancel out, and then we get E plus F minus B. And we have that A is E plus F minus B, and C is negative D minus E minus F. We have solved the basic in terms of the free, and therefore we can write this W in this form. W is just the matrices of the form. Instead of A, I write E plus F minus B. B is a free variable. instead of C, I write negative D minus E minus F. Here we have D, and here we have E, and we have F. But then this can be written as, let's start with the first free variable. B times negative 1, 1, 0, 0, 0, 0, plus the second free variable, plus D times, there is no D here, 0, there is no D here, 0, negative 1, 1, 0, 0, plus the next free variable, E times 1, 0, negative 1, 0, 1, 0, plus the next free variable, F times 1, 0, negative 1, 0, 0, 1, right? Such that B, E, D, and F are scalars. But this is just the span of these matrices. And the matrix negative 1, 1, 0, 0, 0, 0, 0, 0, negative 1, 1, 0, 0, 1, 0, negative 1, 0, 1, 0, and 1, 0, negative 1, 0, 0, 1. Then given a subspace that is written as a set of equations, then we can solve the equations and then we can write them as the span of some vectors. Not that these are called vectors, even though they look like matrices, but since they are elements in a vector space, they are called vectors.